This is part C of the gas laws notes. In these notes, we are going to talk about Charles's law and the temperature and volume relationship. If you haven't yet watched part A of these notes, the intro to gases and modeling gases notes, please go back and do that. In those notes, it talks about our variables of gases and how we can model gases. So Charles' law, the definition of Charles' law is that at a constant pressure, the volume of a gas is directly proportional to its absolute temperature. And absolute temperature just means we are measuring in Kelvin, so we don't have any negative values. We already have our variables defined that we're using Kelvin, and so with this, volume is directly proportional to that temperature. And this is with a constant pressure, and this is with the same amount of gas that is in our system. And so as we look at this, volume of gas is directly proportional. If we have a low temperature shown by kind of this one candle, that means that our molecules are going to be moving more slowly, but they're still going to be colliding with our container. So that is our with that pressure. Pressure staying the same means we need to have the same collisions at our before and after. So to keep that constant pressure, if we have a small volume with a low temperature, in order to keep that constant pressure, if we have more heat, our molecules are going to move more quickly. That means the volume of our container is going to need to expand. And so as volume goes up, temperature is going to need to go up. As volume goes down, temperature is going to need to go down. So directly proportional, they're going to have be doing the same things. And our equation for this, and again, this specific equation isn't on your formula sheet, but within our combined gas law, we see that V1 over T1, volume and temperature, is going to equal volume 2 over temperature 2 with that. And hopefully it makes sense if these need to stay equal. If the volume goes down, this temperature is going to have to also go down in order for that equality to be maintained. If this volume goes up, in order to stay equal, the temperature is going to have to go up. So that is Charles' law. Let's go through some examples. A sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? For this, we do need to remember that because we need our temperatures in Kelvin, Kelvin is equal to degrees Celsius plus 273. That is on your formula sheet, but anytime we're doing calculations, we need to make sure we are actually converting that temperature. So we have a volume of 250 milliliters at 25 degrees Celsius. So volume, temperature. What volume will this occupy at 95? So looking at volume temperature relationship, and we can go ahead and set these as which one is V1, which one is T1, which one is V2, and which one is T2. And then we can go through and kind of assign those. Again, it doesn't matter which one is 1 and 2. It just matters that at the volume and the temperature that we have those paired together. We do need our volumes in liters. So we've got, moving our decimal 1, 2, 3 to the left, 0.250 liters. I'm maintaining my 3 sig figs by putting that 0 after the 5. At 25 degrees Celsius, well, 25 degrees Celsius plus 273, we get 298 Kelvin as our T1. What volume will it occupy at 95 degrees Celsius? We're looking for volume 2. We also need to go 95.0 degrees Celsius plus 273, and we get 368 K. Kelvin is different than Fahrenheit and Celsius. It's not degrees, it's just Kelvin. So there isn't a degree symbol when you're writing those and writing that unit. So we have both of those. Let's go ahead now. We have this relationship, and let's plug those in. So we've got our V1 over T1. I'm going to just plug those in as I go. We've got V1 0.250 liters over T1 298K equals, we're looking for V2 over our 368K, and we need to solve for volume 2. However, algebraically, this makes sense to you. Great, we can look at, okay, let's multiply, let's divide this and then multiply this over. You can also cross multiply and then divide, how I usually will, because it's always going to work. Cross multiply, we've got that 0.250 liters times our 368K is going to equal V2 times 298K. That gets rid of any division we have. And then I can go ahead and divide both sides by that 298K in order to get the value of our volume 2. So however algebraically you want to solve, we just need to get V2 by itself. Go to our calculator and plug those in. Looking at our sig figs, 3 sig figs, 3 sig figs, 3 sig figs. And so we get 0.309. Looking at our units, Kelvin and Kelvin canceled here. We're left with that liters unit, and so that volume is 0.309 liters. Let's go ahead and model this as well. So if we're looking at these, we have volume and temperature changing, but we're going to have in our model the pressure staying the same and the amount of gas staying the same. And so as we look at those, we've got, I'm struggling. So we have the same amount and then pressure is the same, which pressure is collisions. So those are what we're going to need to see. As we look at kind of our before and after, how did we have our variables changing? Well, I've got my volume went from 2.250 liters to 0.309 liters. So our volume went up, and we could have expected that because our temperature went up. And so we're going to show that volume increasing. The volume we show by the size of our container. You could do a circle, you could do a square. So let's just show, okay, there's that volume. After, I'm going to show more volume. So my volume goes up. I show that by the size of the container. Same amount. And so now as I go through and I put in my moles, however many I have before, I'm going to need after. And I just did 5. So we need enough. I kind of want more than like 4 or more than 10 ends up being kind of a lot to have to deal with. Our pressure is the same, which means we need the same number of collisions. So however many collisions I have before, I need after. But my temperature also went up, meaning we are going to have our short arrows before, and then our arrows are going to need to get longer in our after. And that's going to be what helps us maintain those same collisions. So if I've got 1 collision, 2, 3, there's another collision. So this one I'm showing my collisions. Got 1, 2, same number of collisions. So I'm going to want 2 collisions after as well. And I'm going to be able to still do that because I'm going to have longer arrows with my more space. So there's a longer arrow. Make sure we can see Yep, that's longer. You might have a collision with the side where it bounces off. There's one collision though, and then there's another one, two. So we want to show though those same number of collisions, 1, 2. So our pressure is staying the same, amount stays the same, but when I had more volume, the longer arrows show that temperature changed and went up as well. Problem 2. Hydrogen gas was cooled from 150 degrees Celsius. The sample had an initial volume of 0.098 liters. After being cooled, its new volume is 75 milliliters. Assuming pressure remains constant, find the final temperature of the sample. So again, we have temperature and volume variables in this. We're going to have T1 and V1, and then T2 and V2. And we can define these however we want as long as we're looking at the conditions at that same time. So it's cooled from 150 degrees Celsius. That's our temperature. And we need to make sure that we are changing that to Kelvin. So 150 plus that 278 is going to give me 423 Kelvin. The sample has an initial volume of 0.098 liters. After being cooled, the new volume, well, the volume is given in 75 milliliters, but our standard unit for volume is liters, so we need to divide by 1,000, and we get 0.075 liters. Assuming the pressure remains constant, find the final temperature. So we're looking for temperature 2. So as I go through and plug those in, I can also consider my volume is going down, and because this is a direct relationship, we should assume that our temperature is going to go down as well. So let's plug these in. Volume 1, 0.098 liters over T1, 423 Kelvin, is going to equal V2, 0.075 liters over T2, that's our unknown. In this one, our variable is in the denominator, so depending on how you prefer to solve, if you want to do this division and then rearrange, this is a case though when if we do our cross multiplying, we easily get rid of those fractions. We would have 0.098 times T2 equals that 423 Kelvin times 0.075 liters. If you want, you can go ahead and multiply those out, or we can just go ahead and get that T2 by itself. Let's divide both sides by 0.098. And that 0.098, I dropped the unit, but that has liters on it, so our liter units cancel, and then we can get that T2 value. So going to my calculator, I get 323.72. Let's look at our sig figs here. We have 3 sig figs, 2 sig figs, and 2 sig figs. So let's take that to 2 sig figs. We're going to have 1, 2, 320, and then K for those units of Kelvin. All right, that is the end of this set of notes. The gas laws notes will continue in the next video.